Next up, I am very pleased to have Volker Stolz, he's a professor in software engineering at HGL, and he will explain about the formal correctness proofs of refactoring. Please go ahead. Give him a round of
start this. So you will notice one is not like the other here. So but it also, tomorrow is a public holiday, so it definitely feels like Friday at 5:30 for me. I'll make it a little bit light. I'll skip over some of the slides and just show you what is like the key idea, literally key. And then afterwards, the security specialists tell me if this can be useful for you. So this is joint work with my colleague Violet, who's also here, Eduard from Oslo, and a PhD student of ours. And this is based on a 1.5-year-old paper if you want to read all the details. So it's originally an idea to prove correctness of refactorings, that is basically the equivalence of programs. Here's a very simple example, right? So we have an if then else, and well, if you negate the condition, you flip the branches, and hopefully you get the same program, right? So can we actually like mechanically prove that two programs, or even better, fragments of programs are equivalent? Is this really the same? I'll show you a few select examples where it's very easy to trick you, a student, or the IntelliJ refactoring menu in doing source code change that's not equivalent, right? And based on this, then we can discuss how this relates to security. Did we have a laser term? Yeah. Right. So, some secret one.
Okay.
It's working. Yeah, it's just I don't see it. Yes.
Very light.
Yes. Some of the differences between what we've seen so far and what I'm doing, so I'll be dealing with object-oriented programs. And a lot of you have problems with dynamic memory allocation, if I see this correctly, right? So, or you don't do it, you don't care in your protocol specifications. You have other issues. AWS people, and you're chuckling, so you also have your ways of dealing with this, right? So in here, I'll be talking about Java with a full JVM. And of course, there are limitations, but there are also nice things that we do. How does this mainly relate to security? So probably you're going either this way, you have code and a specification, and you have a tool that allows you to verify that your code fulfills the specification, or you go upside down, you come from the specification to something like design by contract or refinement, and you go to code, right? So what I'm doing here is basically going sideways. Of course, there's an underlying specification of the behavior of what Java does, right? But this is like implicit in the tool. I could also slap on JML annotations on my code if I want. But so what we were interested in was like moving along this axis here. I added the word abstract because what we will see is I don't need complete programs to prove something. I can do it just for blocks, individual statements. This whole work is literally standing on the shoulders of companies. The key framework that is underneath is like a multi-year, multi-PhD student effort by various groups in Germany. I think it's maintained by TU Darmstadt and a Høgskulen primarily these days. And on top of this, a PhD student built the Refinity tool, which basically harnesses key to do these equivalence proofs. And what we want to do is we want it as automatic as possible. And that works to some degree. And so I guess I don't have to tell anyone about what program equivalence is. Same input, same output. We do it for Java. What are the limitations? Can anyone do this? And I'll show you what we can do. I think we talked about this, so it's built. It's like two tools set on top of each other. Key is very good in relational verification of Java. I put it in scare quotes because you need a little bit of JML, and there are of course some limitations, but they have had very good success with, for example, finding bugs in the Java SDK, even with this. One of the sorting functions was broken. So just for fun, some other groups were using key to verify, for example, this TIM sort algorithm. That is, it's just a variant on sorting, and they couldn't get the proof to close. Okay, and then they were banging their heads against this, you know, proofs are tricky. And then they realized, no, of course we can't close the proof because the implementation is buggy. So, and then based on the old rule, they wrote a counterexample generator. And then they went to, I must have been the Android list. Because I think they went to Google. And here, this is how we fix it. And then Google picked another way to fix it than the simple one that they suggested. Then they had to shoot another hole into this one, and then finally they accepted a very nice solution that our colleagues have proposed. So it's very, very powerful. Proofs are highly automated up to the point where you do certain things, and then it's the usual serial proofs. So this is the framework this is Refinity, where you can show where you want to show equivalence between the left-hand side and right-hand side. We don't have to read the details. I hope you can make it out here. This one simply says abstract statement A, abstract statement B, and a handful of annotations. This one here says abstract statement B, abstract statement A. Right? So I want to prove, can I swap two statements? Whatever, so basically not statements, even whole blocks. Right? And what are all the annotations? Well, these are the side conditions. Don't look so close. It's a lot of JML, which basically says that you're allowed to swap two statements if they don't interfere with each other, right? They don't touch the same things on the heap, right? And this is all encoded there. So if you give the right specification of what you think your statements do, then the tool will in fact conclude that yes, you are allowed to do this. Right? Then of course one challenge is that if you instantiate this pattern here with the placeholders, some statement block A, some statement block B, with concrete statements, you will have to show that your concrete statements fulfill all these annotated conditions, right? Like not throwing an exception, because if you throw exceptions, you cannot swap the two statements because you would get different exceptions and things like this, right? So there's a little bit of overhead in terms of specification, but if you figure out the right specification, it's really push button. Then Refinity will instantiate a key proof. Key will give you a proof tree with almost 4,000 nodes, and with its heuristics, just squash it. Say this is fine. Right? So here you just see some background output from the underlying key system. So this is like really, really nice. The problem with instantiation, so I showed you, okay, abstract statements, I can swap them with the right annotations. So let's prove a very simple equivalence, creating two objects of different types. I should be able to swap the order, right? New is not going to throw an exception. I'm writing into local variables X and Y, so I'm not modifying any fields, right? And then hopefully we will be able with prove with Refinity that these two programs are equivalent. Yeah, I even zoomed in, yes, so, right. So very simple. It should fit the pattern before, right? And I'm just going to use this as a short insight into how this works internally, something that we can only guess when we looked at ProVerif, right? There was a lot of stuff going on automatically. If you would need your own modifications, what would you have to do? For this system, I can show you based on this example. This actually did not work initially because key is so sensitive that it knows about the heap layout. And it will tell you, no, these two programs are not equivalent because the heaps are different. Because one object, I mean, the order of the objects is like different, right? But there's nothing captured, no exception thrown. So how can we tell key that there's actually nothing going on? Key knows basically the Java language semantics. It has rules for every language construct. And what I just wanted to show you here is the tweak that we have. This is how you would modify or teach key tricks. Some of you have maybe seen these semantic rules. So this here is basically keys representation of a new statement. It's just called allocate, right? I want to allocate an object of class C. I have some context, whatever. S are my remaining statements in the program. And then there's a symbolic representation of the heap somewhere in here, right? It says, okay, we get an object V of type C in the heap. And it's not a subclass, it's an exact instance of, and so on and so forth, right? So a little bit math notation, but it's really just a symbolic representation of what's going on. What was the problem with our swapping two constructor calls? Well, the heap looks different. So with so-called tactlets, like rewriting rules, you can then tell key that, for example, that's easier for me. If we are allocating an object of class C on top of a heap where already something is, but actually this is not the function that is doing the allocation, then I can that did an update to the heap, then I can ignore the store. And you can see that the term from the left to the right gets simpler. Right? The heap H is in here. Here I had recorded some modification of the heap. And after this modification, I allocated my element. And then, okay, this heap modification I can simply throw away if it's not relevant, because we are talking about different objects. And the same thing here. If I'm talking about a heap where I created some object O, and now I'm creating my C, and C has nothing to do with O, then I could, in a sense, just ignore these objects of a type that I don't care about. These are rewriting rules that eliminate things from the symbolic representation of from the symbolic representation of the heap, and then this sails through, right? Of course, so if my theory proving friends are here, then they will ask you, well, are these rewriting rules actually correct? Right? This is something that he doesn't care about. So we have to prove that this change of these rewriting rules of the symbolic representation of the heap are actually correct. You would have to do it on pen and paper. Right? So you're just putting this basically in as an axiom into the system. And we have thought long and hard about this. This behavior is correct. This is an additional rule that then the key system can use in its heuristics. Let me go back and then I'll show you one other example. Little quiz to wake you up. Why are these two programs not equivalent? Should give you a hint. X is an attribute. I call the same method M twice on an object. On the right-hand side, I went to IntelliJ, refactor, extract local variable, and now I'm calling this the variable temp. Yeah, it's a reference, but what could the problem be? It's calling the same method on the same object. Or is it? Because if n has a side effect in the left-hand side program, that it modifies x, right? If x.n modifies the x, then these two programs are not equivalent, right? And if you put this into Refinity, then it will actually point this out to you and say, hey, there's an open goal, and of course there's no way to around it, but no way around it. You have to say, oh, this is only valid if I don't modify any attribute that is my calling object, right? So as usual, the theorem prover is a very good assistant in looking over your shoulder and slapping you on the wrist when you're trying to take a shortcut. Right? It's very good at bookkeeping, and then it's up to you. Well, does my method n actually have this property, or does it not? Right. So yeah, we can encode this in Refinity with some assertions just to give the types, and then we will get exactly this error method, and we will have to provide these annotations that basically the statement, the variable x must live in a different part of the heap than the one that the must touches. This is just how it's represented. Like I said, JML with some extensions. Okay, I'll quickly wrap up. So we use this for refactorings. You know Fowler's book. made, right? So many patterns that you should apply described in natural language. And if you try to formalize them, then you get like pages and pages of excite conditions that Fowler usually summarizes in item 1, think very hard if the program really does the same thing afterwards as before. And you should have test cases, right? So, but here you would have to write these conditions. Yeah. Okay, so internals, I showed you a little bit. So this is, for example, a symbolic representation of the heap. And yeah, so the internally key uses heuristics. It's fine-tuned for to be good at a lot of things, and sometimes you may have to do manual steps. You could see it on the slides if you go back. So yeah, you were all talking about protocols. So this is actually what we wanted to look at next, right? So everything that we could do with key was talking about heap modifications, variable modifications, invariants, things like this. So what we really want to do is we want to also be able to reason about sequences of method calls, right? Behavioral types. This is what you could do like with maybe with pi calculus, with session types. People have many different frameworks, so this is nothing new. We just want to try and make it available in this tool so that I could specify that in my abstract statement A here, for example, I can do whatever, but I must call open on this particular file, right? And this, when I can do something, and this other statement, abstract statement, it must close this file so that I can have regular expressions basically over an interface that then particular statement blocks should adhere to. We can try extracting this from the source code, right, and verifying it. We have a lot of success with runtime verification, for example, using aspect-oriented programming to make runtime monitors for these permitted sequences of calls, especially in Java. It's like super easy, right? But statically, that's always a little bit tricky. So yeah, so if you have to deal with real programming in an object-oriented language, here Java, then I invite you to take a look at Key. It's really good at what it does. You specify concrete code, abstract code, side conditions through annotations. You can use Key to verify algorithms, Refinity in particular for equivalent code. And now the question is, of course, how can we, this is in any way relevant for security, right? So it's a very general technology, right? So maybe we see something. For me, the motivation was, if you have a working version and you make changes, do you want to go through all the proofs that you maybe did again, or can you just maybe an easier way to prove that the new version behaves like the old version with such a framework? Thank you for your time.
That's Java specific, like what you presented. Is it possible, or how would it be to target other languages?
With this framework, probably impossible. I don't think this can be customized in any way. The nice thing is the group in Darmstadt got the DFG grant on at least on the maintainer of this framework, so that they continue to support it. But for other languages, I think for C, someone did interesting stuff through functional languages. I can't remember the name, but there was like a version that encodes C programs in Haskell and then runs those. And then I don't know if you could do any analysis there, but if you like annotations, you could use pharmacy. That is industry standard, for example, in smart cards. I know many people use it. You have C code, you have annotations and tool support. But like for C++ for object-oriented languages like C++,
Thank you.
Not even Scala.
so
Not even Scala.
Scala, interesting, right? Because it's on the JVM. Probably you would just need a different front end, and you would need to do all the things that Scala does before it gets to Java bytecode. As far as I know, unfortunately, he doesn't work on Java bytecode. It works really on the Java syntax. So unfortunately, that would probably be a little bit too complex.
Okay, so let's thank the speaker again.
We still have around 36 hours to submit to the workshop on security of software and hardware interfaces, together with EuroSP later this month. And when they say Friday night, they probably mean Monday morning.